All right, girls, here are the notes for section 8.4. These notes are all about hyperbolas. The good news with hyperbolas is that you've already done ellipses, and there's a lot of similarity between the two. The graphs of hyperbolas look really intimidating, but I promise you that if you can do ellipses well, then you'll be able to do hyperbolas. Okay, quick reminder from section 8.1 that hyperbolas are always going to have one squared term that's negative. So if you see a subtraction of y squared or a subtraction of x squared, then that's going to trigger to you, I'm doing a hyperbola graph. Okay, just like with circles and ellipses, the center of a hyperbola is also HK. A few other things that we've already learned from ellipses: A is the distance from the center to the vertices, B is the center to the co-vertices, and C is the distance from the center to the foci. All right. Now, it's going to seem strange, but A is the distance to the vertices. The vertices will be on the graph, and the co-vertices will not be on the graph. The co-vertices are still important, and you have to find them when you're getting ready to draw the graph. I'll show you that in a second, but the graph will not actually go through the co-vertices. A few other things is that A does not have to be bigger than B in a hyperbola. You found out that that's kind of one of the keys to doing the foci for ellipses. But if you notice, the equation for finding the foci is actually a squared plus b squared equals c squared. So it doesn't really matter. You're not going to end up with a negative if one's bigger than the other. And it's not going to matter in the graphing either. A is allowed to be bigger or B is allowed to be bigger. Doesn't matter. Okay, so there's two ways that a hyperbola can go. The first is horizontal, and that equation looks like this: x minus h squared all over a squared minus, because it's a hyperbola, y minus k squared all over b squared equals 1. Okay, really similar to an ellipse equation, except for that subtraction symbol in the middle. If the y squared term is negative, if you want to think of it that way, or the x squared term is positive, it's going to be horizontal, which means that the hyperbola is going to look like this. It's going to be opening to the left and to the right. All right, for this example, let's go ahead and graph this equation here. X minus 3 squared over 9 minus y minus 3 squared over 16 equals 1. Okay, just like an ellipse, you're going to find the center, which is 3, 3. You're going to go 3 in the x direction and 3 in the y direction. All right, now I already know that this is opening left and right, so that's going to trigger to me that this is going to be a vertex and this is going to be a vertex. I'll go 4 in the y direction. This is a co-vertex, and like I mentioned, will not be on the graph. Okay, now it kind of looks like you've just created a little ellipse, but you are not going to draw this ellipse in. What you're instead going to do is notice that this is a rectangle, and what's really important about the rectangle are the corners of it. So if you were to sketch out a little rectangle with the co-vertices and vertices being the midpoints of the sides, it would look like this. The really key part is the corner of each of these, the corners of the rectangle. Okay, the reason those corners are important is because those are going to be the asymptotes of the hyperbola. So you just put some dotted lines through the corners of that little box. And remember, an asymptote is a line that a graph approaches and never touches. So those corners give you those lines, and those lines give you the shape of your parabolas. There's no latus rectum in these. There's no P defined. All you have to do is draw that rectangle. Realize which ones are the vertices. Remember, the graph goes through the vertices. I know the left and right ones are the vertices because of the way that the equation is written. And then I draw my hyperbola in. And it You get really close to those dotted lines, but do not cross the dotted lines. And there's your hyperbola. Okay, in order to find the foci, remember the equation is going to be a squared plus b squared equals c squared. So a and b don't really matter. A is technically 9 in this problem, or 3 squared. I'm sorry, a squared is 9 and a is 3. B squared is 16 and b is 4. So this is a and this is b. And then, of course, I can do the Pythagorean theorem, and I get 25 is c squared, so c must be 5. Remember, c tells you the distance from the center to the focus, and the foci are always going to be outside the vertices. Wherever the vertices are, the foci will be right outside them. So from the center, I'll count out 5, and this is a focus. And this is a focus. And you're finished. Okay, let's take a look at the next one. The next one we'll do a vertical hyperbola. How you know that it's going to be a vertical hyperbola is the way the equation is written. So in this, you're either going to have your y squared first, and it's going to be positive, and your x squared second, and it will be negative. Or if the x squared isn't second, then it's just going to have a negative at the very beginning of the equation. So be careful because these two things here can flip-flop, but the key is that the x squared is the negative one in this case. Okay, so this tells you it's going to be vertical. So it looks like this. And let's do an example of this one. So let's do y minus 2 squared over 9, x minus 1 squared over 25 equals 1. Okay, the center of this is going to be, remember you have to be careful on these when you're writing the center. It's going to be 1, 2, right? You have to look at it. X comes first. So 1, 2 is the center. I will go 3 in the y direction. And I know that those are going to be the vertices because the vertices are always on the graph and this opens up and down. So those are my vertices. Then I'll go 5 in the x direction and those will be the co-vertices. Okay, once again, it kind of looks like I've graphed an ellipse, but those are the corners of a little rectangle. Not the corners, just the midpoints of the sides of a rectangle. What I care about the most on that rectangle are the corners. So this corner here, 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 and here. The reason I care about those corners is because the asymptotes go through them, and the asymptotes are what help me graph my little parabolas, which are part of the hyperbola. So I'll go through the vertex, it's up and down, and I'll get close but never cross them. So this is a really wide, fat hyperbola. All right, the foci in this problem, remember it's c squared equals a squared plus b squared. Again, it doesn't really matter for the algebra here which one is which because it's an addition problem, but the vertices are technically a. And so that's 9, so 3 squared or 9. The co-vertices are b, so 5 squared, which is 25. And when I do the math here, I get 25 plus 9, which is 34. So c, the distance from the center to the foci, will be the square root of 34. Now, that's not a pretty number, so to help me graph it, it's approximately 5.83. So I'll go about 6 in each projection from the center. 1, 2, 3, 4, 5, 6. That's a focus. 1, 2, 3, 4, 5, 6. That's a focus. Now, remember the coordinates of those foci I can write as an actual point. So if I take the center of this, which was 1, 2, all of those points, the foci, the center, and the vertices are all 1 unit over. So that 1 is going to stay. But I took 2, which was the center, and I added root 34 and I subtracted root 34. So that was kind of a hard part with ellipses, but now that we've done it, it's really the same for hyperbolas. Okay, I'll show you how to write some equations in the next video.